Good morning all. Myself Dr. Deepak Yadav, Assistant Professor in Akgec Engineering College, Ghaziabad. And today we are going to discuss one of the complex topic of digital system design subject, that is analog to digital converter. So to understand how the analog signal is converted into digital signals, first we have to understand the process of how the analog signal goes through different processes to convert it into analog signal. So the first process is to limit the amplitude of the incoming analog signal with the help of different limiter circuits that fix the amplitude between a certain range, like from -5 to +5 volt, and then with the help of sampling process the signal is sampled first over the time domain, and then the amplitude is quantized with the help of different quantization level provided to the signal. So here for the voltage conversion, we generally used different type of analog to digital converters. So these are some example of analog to digital converters. We classified these converters with the help of different speed, how to change the how the integrator or the analog to digital converter respond to the speed, as well as the high accuracy of the analog to digital signal. So if we use integrating type analog to digital converter, the speed is from low to medium, that is, it takes time, but the accuracy is very high. While if we use medium speed analog to digital signals, the speed is minimum and the accuracy is minimum, and we use for this kind of operation successive approximation type converters is used. While for the very high speed but very low accuracy or medium to low accuracy, the flash type converters are used that convert the incoming analog signal directly into digital signal. So the first one is the integrating or dual slope analog to digital converter. So in analog, why it is called dual slope? We deal with this two type of slope, that is, first for the input incoming signal, and the another slope is for the reference signal that is already fixed, and for this fixed signal the slope of the integrator output is fixed again, like it is the complete process is converted into two category or divided into two category. The first one is the phase 1 and the another is phase 2. So in the phase 1, the integrator integrate the basic input signal that we want to convert into digital one. So for this, the integrator, which is having the capacitance C1 and the input resistance R1, the input signal is now integrate with the help of this integrator for a fixed amount of time, and it is represented by T load over here. So the output voltage generated at the output terminal of the integrator is equal to the input voltage divided by R1, this resistance, multiplied by the time taken to generate this amount of voltage at the output terminal. So this time is variable. Anyone can take any time, like for 10 seconds or for 15 seconds for the integration. And in the phase 2, now this switch to the reference voltage, which is having the negative magnitude. As in the first case, the voltage, as the signal is integrated, constant signal is integrated, it is converted into slope and it is going increasing in a linear fashion, as we can see over here. So at the output of the integrator, we have a fixed amount of voltage. So to convert this voltage again back to the reference zero voltage, we need a negative polarity of the input reference voltage, so that the magnitude now goes down from maximum, from a fixed value to a zero value. So for the phase 2, the integrator circuit take the reference voltage minus V reference and reference it and integrate it up to V output voltage, that is V is equal to 0 for a fixed number, in the fixed time at delta t time. So that output voltage that it is going to be integrated is equal to minus V reference divided by R1 into time interval T1. So if we compare these two equations, we find that the output incoming input voltage in terms of reference voltage and the time, that is the fixed time that is taken over here, and the variable time that is taken in the second phase. So the the magnitude of the input voltage is equal to the magnitude of the reference voltage that we are use over here, multiplied by the time taken of the reference voltage, multiplied by divided by again the total load time in the first phase. So as we can see over here, this is the phase 1, this is the phase 2, and this is voltage and time plot. In the first phase, when input voltage V in input voltage is given, so for the different magnitude of V in voltage, so as the V in voltage magnitude is going increase, for the fixed amount of time, the integrator output is going like this. For the lower voltage, for the higher magnitude voltage is going like this and like this. Now we fix the RC constant of the integrator, so the slope became fixed with the help of the fixed reference voltage, and now the output voltage is integrated with respect to the reference voltage, and it take a different amount of time for the different magnitude of the input signal. So for the first, like for low voltage signal, low amplitude signal, the time is delta T1. For medium became T2, which is greater than T1, and for the third one, for higher amplitude of the input signal, it is equal to delta T3. So one of the disadvantage of this integrator is that the time is variable. For the different amplitude of the incoming signal, the time taken by the dual slope analog to digital converter had different values. So it is not a fixed time output provider. It provide the output signal with respect to in time with respect to the amplitude of the incoming analog signal voltage. So this is some pro and cons of this integrating type analog to digital converter. Simple structure is very simple, as we can use only one comparator and one integrator circuit, as we can see over here. This is one integrator circuit and this is one comparator circuit, and a counter is required for converting the magnitude that is coming from the comparator output. And another thing is low area and low power. So as very few circuit is used, only one counter, one control system and two comparator, two 741 ICs. So the area occupied over the chip is very small, and again as the component is minimum, it takes a very less power. The disadvantage is slow. These kind of analog to digital converters are very slow, and it takes variable time. The time is not constant. It takes the variable time for the different input of the incoming signal. The work of the counter over here is that until the magnitude became 0, the comparator output is high, and this counter is counting until it reaches to 0. So the count duration is fixed. So whatever the amount of the time is, if the time is larger, the count goes the larger values, while if the time is smaller, the count goes to smaller values. So the digital output is directly proportional to the incoming input signal voltage. If input signal voltage is less, the output is output count is very low, while for the high values the output count is very high. Now the another one which is used as an analog to digital converter is successive approximation type analog to digital converters. So in this, a digital to analog converter is first used to convert the generated output, that is generated digital signal into analog signal again, and this converted analog signal is again compared with the input signal with the help of this comparator IC. So the thing is, first generate internal analog signal with the help of digital to analog converter, that is equal to VDA. Then this VDA is compared with the incoming signal Vin, and the comparator output is now provided a particular bits to the to generate the digital signals. Comparison with the help of comparator with Vin, and then modify the count D0 to Dn minus 1 until the closest possible value of Vin is not reached. This count is updated and updated again and again in every cycle, and the process goes on until the count that is almost equivalent to Vin is not reached. So how this comparator work? The input signal is applied, and this input signal is compared with the digital to analog output. From here, digital to analog output, the first most significant bit is set to 1, so that the reference signal VDA output is equal to V reference divided by 2, as we can see over here, and then the input signal is compared with the V reference divided by 2. If the magnitude is less than, the input signal magnitude is less than V reference divided by 2, the path goes in this way, and if it is greater than input signal voltage is greater than V reference by 2, then the path goes in this way. In this case, the most significant bit is set to 1, while in this case the most significant bit is set to 0, as we can see over here. The input signal is compared with the 1 by 2 of V reference, and the most significant bit is set to 1, and when and it is now converted into 2 branch. The most significant bit is 1 over here, and the most significant bit is 0 over here. Now again, if the magnitude of the input signal voltage is less than V reference by 2, the again comparator convert this digital to analog converter convert this signal, and which is less than V reference by 2, and this signal is again compared with the input Vin signal, and again 2 case is generated. Again, if V reference is less than Vin is less than V reference by 4, or another is if the V reference is greater than input voltage is greater than V reference by 4. Again, in this case, let's suppose if in the first case, if the V reference is greater than, input signal is greater than V reference by 2, in this case the comparator output is set to 3 V reference by 4, that is 75% of the V reference, and again 2 cases generated, that is if the Vin is less than V reference by 4, 3 by 4, and is greater than 3 by 4. So again the bit is set for 1 over here and is set for 0 over here, as we can see over here. For the first case, this is 1 and this is 0, and for the second case, when it is greater than V reference by 2, then the comparison is between the voltage is greater than 3 times of V reference by 4, or less than 3 into V reference divided by 4. So in this case, the most significant bit is set to 1 only, while the second most significant bit is set 1 for the input voltage which is greater than 3 by 4 of the V reference, and set to 0 for the value which is less than 3 by 4 of the V reference. Now again this count is again converted into two part further, 1 and 0. So the 1 and 0 is provided for, like for this case, if both most significant bit is high, then again the last significant bit, that is the signal is lying between 7 by 8 and 6 by 8 of this, and we get 111 for the most significant bit, then 110 for the voltage that lies between this range, and 101 for the voltage lies in this range, and for the last 000 when the voltage is lying below V reference by 8. So as we can see over here, if we go in the negative direction, this most significant bit is 0, when the next most significant bit may be 1, and this one goes over here, and if it is less than 0, it goes over here, that is as a 0, then 1 and 1, and these are the outputs. as we can see over here. So the voltage lies between these ranges. Now if we take an example, let's suppose if the voltage is voltage V in is in this range. So for the first comparison, the voltage is greater than V reference by 4, and then it crosses V in, it crosses the 6 by 8 limit over here, and then again goes down as the comparison, as the reference voltage is greater than the input voltage goes down, and it settle into some fixed value, and the corresponding digital count is provided to this one, as we can see over here. First goes up, then goes down with the help of comparator, and then goes up, and we have the output 101. So in this way, in the successive approximation type analog to digital converters, the most significant bit is set to 1, and then the least set to 1, and then one by one the bit is set, and the signal is converted into analog, and again further compared, and until it goes a fixed value which is more close to the input voltage. And this is known as the error that is lying when the analog signal is converted into digital one. So in this case, again a very less number of component is used, so very low area is used over the ICs, and low power again consumed. The disadvantage is high effort of digital to analog converter. So in this analog to digital converter, we already use a digital to analog converter. So this is again a very complex circuit. So if we going to use this again slow down the process of the complete analog to digital converter. So that's why this takes more time as well, and the circuit is little complex as well. And early wrong decision leads to the false result. If somehow if this comparison or one of the comparator work wrong and provide, like for the least significant bit became over 0 over here, complete result goes out. So it's depend upon the previous result or previous state of the circuit as well. So that's why the chances of the error is very high in successive approximation type analog to digital converters. The last one is flash analog to digital converter. Why flash? Because this comparator is very fast. It provides a result in a very fast manner, but the accuracy is little low. In this case, an encoder is used that provide the output count, and output count, like let's suppose if we take the 3-bit output, then we need a 8:3 encoder circuit. 8:3 encoder circuit that provide the 3-bit code at the output, and 8 input pin from 0 to 7 as the input. Now for each input pin there is a comparator which is over here, and the input reference signal is divided into 8 subcategories over here, as we can see. R and R by 2 ladder is over here, and the reference input signal is provided over the second terminal of the comparator. So if the reference signal is very less, like it is less than or it lies between, let's suppose it lies between the range, input signal lies between the range V reference by 8 to 0, like in this range. So in this case this became 1, and the voltage which is greater than this became 1, and this pin is set to 1, and rest of all the pins are set to 0. In this case the code generated is 0, 0 and 0. So if the voltage lies in this range, only the least significant bit of the 8-bit input is set to 1. Like if we have the 8-bit input 3, 4, 5, 8, this is set to 1, and the rest of the pins are set to 0, and the output is 0, 0 and 0. While if the reference voltage is greater than V reference by 8 but less than V reference into 2 by 8, between this range, in this case this comparator and this comparator works, which provide 1 and 1 output, and rest of the pins are input. So these pins are 0, this is 1 and this is 1, which provide the output is equal to 0, 0 and 1. So in this way, as the amplitude of the V input signal is increases, the corresponding pin that is below to that reference voltages goes high for the comparator, and rest of the pin goes low for the comparator, and the corresponding digital count is provided at the output of the encoder circuit. So as the signal is applied, the comparator respond and the corresponding code is generated. So it is very fast. Only the propagation delay of the comparator and these gates and the encoder are included in the conversion time. Otherwise these comparator are very fast. But the problem is, if the voltage lies between the two comparison level, like the voltages lies between 7 V reference by 8 and 6 V reference by 8, if any voltages lies between these two values, then the output is either up or down. So the error is very high in flash type comparator. So that's why these comparators are used, this analog to digital converters are used where the high speed is required but very less number of accuracy. So in this way, this converter is used for converting the analog signal into digital one. So again, the advantage is it is very fast. The problem is high effort of 2 to the power n comparators. Here 2 to the power n comparator is used. So as we increase the accuracy, the number of comparator is increases, which alternately increase the area on the chip as well as the circuit cost, because the number of the component going to be increased over here. Large area and high power, as the number of component is very high, high power is again used in this kind of ICs, and it is recommended for up to 6 to 8 bit or less, not greater than 6 to 8 bit, because the number of comparators and the required encoder circuit is very complex in this case. If we goes from 8 for bit which is greater than 8, and this became a very complex circuit. So we recommend for up to 8 bit. And thank you. So these are the 3 converters that we use, analog to digital converter that we used in converting the analog signal, analog voltage into digital voltages. Each of it's having its advantage and disadvantages, as we can see over here. So this is all for today's lecture. Thank you.